recording. Excellent. Okay, last chapter, and this is what we need to finish off the last lab, integrated circuit bus. We've talked about three main methods of communication in the third part of the course: UART, SPI, and now we're going to talk about I2C, or integrated circuit bus. And high level, this is all you need. You need a bunch of devices and two wires. The only external components you need are some pull-up resistors. Okay? And that's it. So I2C is, oh, I just remembered the joke I put into this lecture. It's always right about this slide that I remember. You can go back and look at last year's video. I have the same look of utter joy on my face. So each of these devices connects up in parallel to the same two lines. One is called SDA for serial data, and the other is called SCL for serial clock. These are all serial communication streams, whether it's UART or SPI or I2C. It's all serial communication, one bit after another. Big shout out here, you must have pull-up resistors to VCC on both of these lines or nothing works. The metaphor that I keep coming back to what is this? Somebody said it. Somebody got it. Don't pretend like you don't understand my art. It's a balloon. It's a balloon. Somebody holds a balloon. What happens if they let go of the balloon? It rises, right? Why does it rise? Because we have lots of helium inside of this, and outside we have nitrogens, oxygens, nitrogens, oxygens, some carbon dioxide. Now, if you let go of it, it rises because helium is lighter. What happens if there is another person, say a really nasty sister, who thinks that it should have been her balloon? Now, what happens if you let go of the balloon but she doesn't? Does it fly off into the air? No. Okay. Flying off into the air is a 1. Staying held to ground is a 0. Just keep this metaphor in mind. I promise it's the best way to understand what's going on. So you've got this balloon. This balloon represents a bit. It's either going to float up into the air or it's going to be held down. The idea is each of these is a little bratty sister or brother that is holding on to the bus. Each one of these is a balloon. All right, and then there's you over here, and you want to communicate with, say, that bus. You can do that. And when you are holding the balloon, nobody else can take control of the balloon from you. Okay? Quickly, what's going on here? On your typical TTL output is what we call a push-pull. And a push-pull has the ability to get to both positive voltage and to ground. It has the opportunity to produce both of these at the output. It does that with two electronically controllable switches, usually some sort of FET. Okay, and if we close that switch, then we have 5 volts going to ground and 5 volts going to the output, and no connection to ground, so current flows out of there. If we closed the other switch and left this one open, we would have a direct connection to ground, no connection to 5 volts, so current could sink to ground. Everybody's okay with the way that works, right? We either provide a connection directly to ground or directly to VCC. Parasitic capacitances and series resistances notwithstanding. This is an idealized case, no resistors, no caps. Current either goes in or comes out. The other way that we can create this, and the reason we need the resistors, did I do it right? Pen, ink, color. Open, excuse me, wrong one. Open collector. Open collector means we only have a single switch to ground, and that's it. So we have no way to pull it high. Push-pull will either push or pull to 5 or ground. But open collector says there is no high side of this. What does that mean for us? Well, it means if we close the switch, we definitely see 0 volts. If we open the switch, what do we see? Where is 5 volts anywhere on this page? Nope. 0 volts isn't connected. It's open. So there's no connection anywhere. The magic word I'm looking for here starts with an F. Floating. Or high Z. Remember, we talked about high Z way back when. We were talking about I/O. It's not connected to anything. No current flows anywhere. And we dealt with this already because we've already built this circuit. It's a button that goes to ground and then goes into the microcontroller. And what does the microcontroller have inside of it? Specifically when we're talking about the button. Remember B7 connected to a button? If you want to actually deal with the button or the button keypad.
This is the thing where we have two pieces that communicate over each other?
Nope, this is just a button. We need to somehow make this show both 0 and 5 volts. Right now we can only make it show 0 volts. There you go. Say it loud so everybody can hear. A pull-up resistor. That internal pull-up resistor. So now when the button is not pressed, small current can flow that way. When the button is pressed, we're still at 0 volts and a little bit of current flows to ground. Yes. Yes. So we call that wire anding. Multiple devices are on the same thing. So if any one of these devices brings the bus low, means holds onto the balloon, everybody else can release the bus, release that switch. You're done with Thanksgiving videos now, right? Okay. If anybody else releases this, they're just Z-stated. So he's Z-stated, Z-stated, Z-stated. That's pulled low. So what does the whole wire look like? What is the voltage on that wire? 0. There is no way to create a 5-volt output from any of these devices. So what happens if I Z-state the last one? The whole thing is connected to nothing except the pull-up resistors. So that's what causes it to actually go high. Okay? And we can have up to roughly 127 devices, depending on how you address things. Unfortunately, this is the easiest one to actually work through because there is a standard way. Unlike SPI, if we have multiple devices on SPI, you need clock, MISO, MOSI, plus however many select lines as you have devices. So it gets wire intensive after a while. I2C up to 100 devices, all using the same 2 lines. So there's a higher level communication protocol, higher than the physical level. At the packet level or the frame level, we talk about how to talk to different devices. The problem is, you'll notice the arrows. A lot can be read into just from this diagram. This diagram has arrows at both sides. What does that mean in terms of our communication? Is this an input or an output? It's both. It's bi-directional communication. So let's talk about this for a second. 2 new words that we have to deal with. We have to drill not only with master and slave, because those both still exist in I2C, but now we have to talk about transmitter and receiver. And the way this works, a master will always be the master, the slave will always be the slave, but the master will not always be the transmitter. Sometimes the slave will be the transmitter. Okay? Unlike SPI and UART, which have 2 data wires per full duplex communication, okay, this has only 1 data wire. So the transmitter and the receiver tell the direction of travel. The master and the slave have to switch off who gets control of the data wire. And this gets really confusing because unlike most things, we don't deal with powers of 2 in our data transmission. We actually have a 9-bit transmission. Everything is done in groups of 9 bits. And to make matters weirder, the first 8 come from the transmitter. The last bit comes from the receiver. Unfortunately, much like the rescuers, you can't see it or touch it. You only see 1 wire, so you don't know who is actually producing these waveforms. They are aggregated together. Let me give you a quick example of how that aggregation works. 2 devices, eventually they're connected up to the same line. The only thing they can produce is a 0 or a high Z, a 0 or a high Z. On the line, we do have a pull-up resistor. So let's just say that the first one outputs Z, Z, 0, Z. That's the number 13. They wanted to do 1, 1, 0, 1. Now let's also look at this one, Z, 0, 0, Z. They tried to transmit at the same time. First off, nothing blows up because we're not shoving 5 volts into any of the zeros. Okay? But what happens when you take 2 Z's and you output them? What appears on this output node here? Well, no. Z appears here, but when you add in this thing, well, logical 1, yeah, 5 volts. Becomes a logical 1. What about when we take Z and 0? It's a 0. The Z lets go of the balloon, but the 0 is still holding onto that balloon, so it stays low. Now, what happens when both of them are 0? Is there any conflict there? No, they're just both holding onto the balloon. It's at the same state, so it's a 0. And now we're back to ZZ. So what does that cause? A 1. So interestingly, even though this guy tried to transmit a 1, 1, 0, 1, this guy tried to transmit a 1, 0, 0, 1, we got out a 1, 0, 0, 1. This is the idea of a wire AND. You only get a 1 if both outputs are outputting what they think of as a 1. Okay? So the protocol itself says, hey, you're going to have 8 bits coming from the transmitter. To red. 8 bits come from the transmitter, and then there'll be what's called an acknowledge bit from the receiver. Now that acknowledge bit is either going to be a 1 or it's going to be a 0, depending on what kind of a message you want to say. All right, if you're trying to acknowledge something and saying, yes, okay, I'm happy, I agree with that, you send a 1. If you say, no, I don't really want to do whatever it is you just asked me, you send a 0. In certain cases. What I want to say is that not acknowledging something is not an error. It just means that you've decided to not acknowledge that their presence. Much like I don't usually acknowledge George when he's here, right? Doesn't mean he's not here. It just means I'm not acknowledging him. All right. So here we go. We've got this data line, and that's what goes on in the data line. Furthermore, there is a clock. The clock is just like you'd expect from an SPI transmission. On edges, it does something. All right. How that works is slightly different, though. Data is said to be stable when the clock is high, and it is said to change anytime the clock is low. So data will only changes when the clock is low. It is stable when the clock is high. And that's it. Okay? So you could think of it as you can read it on a rising edge or just after a rising edge, and you can change it when it's a falling edge. but really it is level sensitive. You read in the middle of this clock and you will see the data. You change it in the middle of the low part of the clock and you're good to go. Now there's one big exception, okay, and it's called a start condition and a stop condition. These are what we call data bits. So if it's one of these data bits here, that's what we're talking about. It changes on the low and it's stable on the high. This is all physical level details so that when you look at this on a logic analyzer, you know what's going on. All right, so the start and stop conditions are the exceptions to these two rules. They break them explicitly. When the data changes and the clock is high, that's called a start condition. When it goes from a low to a high, that's a stop condition. So high to low while the clock is high, that's a start condition. Low to high while the clock is high, that is a stop condition. The reason these conditions exist is because this is a parallel bus. Lots of things are on this bus. I go back here. You've got all these things that are on this bus, and that's fine. But because we've separated out the idea of master versus slave from transmitter and receiver, device 1 could talk to device 2 or talk to device 3 or talk to device N. Device 2 could talk to device 1 or device 3 or device N, and so on and so forth. They could talk to anything. Any device on this bus can talk to any other device. So you need to have this ability to understand when the bus is free, okay? Because if you're talking, device 1, say, is talking to device 2, and device 3 decides it wants to talk to device N, that's not allowed at the same time because it's a shared resource. This is shared across all of them. So device 3 has to wait until device 1 and device 2 are done talking. How does it know when it's done talking? It sees a stop condition. That's it. So that's why we have start and stop conditions. But what if device 1 needs to get several pieces of data from device 2? It doesn't want to give up control of the bus. It has to get all of this stuff all at once. Maybe this is some mission critical sensor. Okay. What we do is we provide the opportunity to create, where am I? A repeated start condition. So in a repeated start, you do a start condition. A bunch of data stuff happens here. Then you do another start condition. That resets the bus and all of the things listening to it. So you can stay the master of the bus until you give it up. It's not fair, okay? It's a quality of service issue. You can starve out everybody else on the bus just by doing this kind of dick move right here. But there's a reason, okay? If you need this data and you need it now, you can't get the first upper bite of a temperature in, say, a furnace, and then something else goes off and finds the weather out today, and then get the second bite. You need both bites at once. Okay, so that's what's going on with a repeated start. Each of these is going to be part of a higher level protocol. So we've got data bits, start conditions, stop conditions. Repeated start conditions really are just the same thing as start conditions. That's the physical level. Things go high and low. The next level up from that, in terms of abstraction, is the packet format. A packet is always 9 bits long, bless you. Okay? The first 8 bits come from what we call the transmitter. That does not mean it's the master. It just means it's the guy that's going to be sending the data. So the first 8 come from the transmitter. The last comes from the receiver. Regardless of who the transmitter and the receiver are, the master device transmits the clock. So the slave might be the transmitter, but the master still generates the clock. And again, that acknowledge or not acknowledge, either it leaves it high or it pulls it down. Now that packet is used at the next layer of abstraction because there's actually two different types of packets. They're the same physical format, 8 bits plus an acknowledge bit. Okay. We've got an address packet and a data packet. Address packet says, hey, I want to talk to you, or you, or you, or that guy. Okay. We had devices 1 through n. It tells you which device you want to talk to and also what you want to do with it. The data packet is actually data going back and forth. It's very generic. So let's look at the address packet. It follows the rules of 8 data bits plus an acknowledge bit. Because you can communicate with up to 128 devices, okay, really 127, you've got a 7-bit address. So the first 7 bits are the address of the device you want to talk to. The last byte is what we call the read-write byte. It tells the device whether you're going to be asking it for data or giving it data. So you might be sending it a command. You might be receiving a sensor reading from it. The last thing comes from the receiver. In the address packet, it says 1 for yes, I'm on the bus, I'm here. It's the equivalent of Ferris Bueller's Day Off. Bueller, Bueller, Bueller. Why does dumb question, why does the professor keep mentioning Bueller's name? If he's sleeping, but why is he saying names at all? What's he doing? Yeah, say it again.
To make sure they're there.
Yeah, what do you call that when a teacher checks to make sure each student is in class? Attendance. What?
Sanity.
Sanity. I don't care if you're in class. That's right, attendance. So he kept saying Bueller because Bueller didn't respond with here, that acknowledge bit. That's the here in this case. It's the response from the student or the slave, basically the same thing, that says, hey, I am present on the bus. So if you send out an address packet and don't receive an acknowledge on the address packet, this only applies to the address packet. If you don't get an acknowledge, chances are the chip's not there. You're talking to an empty classroom, okay? So there we go. That's an address packet. A data packet, it's very generic. It's 8 bits of data and a 9th bit. Either an acknowledge or a not acknowledge. Now, in a data packet, acknowledge and not acknowledge do not mean error. They don't mean not there. It's not necessarily an error. It's some kind of status. When we talk about some of the I2C devices we're going to be playing with, especially for the alarm clock lab, you'll see that acknowledge or not acknowledge means something to the slave device. So we've got these 2 different packets. A typical transmission is an address packet and then 1 or more data packets with a start and a stop bounding them. And that's it. That's all there is to a typical data transmission. You say, I want to talk to Adam. Adam looks up at me scared. That's the acknowledge part. Okay? And then I say, what is the square root of 325? That's his data. Doesn't matter. He doesn't have to give me correct data. It's just a data packet. Okay? It could be that I'm asking something that doesn't do math to do math. And that's you, basically, in a nutshell. All right? So that's a data packet. You can have 1 or more data bytes. Okay? But in either case, you're going to be either reading those bytes or writing those bytes. Oftentimes, first, you have to say, Mr. Memory, set your pointer to address 100. That's a write command. Set your pointer to address 100. So you're talking to a memory. Mr. Memory is the address, write, and then the data byte is 100. Then you say, Mr. Memory, read 10 bytes. So you will receive 10 bytes. You're doing a read, talking to Mr. Memory. Now, why did I send the address packet twice? Why would I send the address packet twice? Because if I'm going to be doing reading and writing, one transmission can either be all reads or all writes, not both. So what would be good? So here's the start condition. Here I'm done, so there's a stop condition. What do I have to put in between these two lines? A repeated start, R start, because I don't want to let go of the bus. This is a very common phenomena. First, you tell the memory, set your internal pointer to a particular address. So you write the number 100 to this device. It knows, okay, now I'm looking at address 100. Then when you read, it starts sending bytes sequentially. Okay, so that's a very good example of why you might need a repeated start condition. Now, another thing that you might do with an I2C device, we're going to use Adam because he's today's whipping boy. Adam, what's the square root of 25? That was pretty fast, right? You were able to tell me immediately. What's the cubed root of 125? You paused for a little while there. You weren't quite ready to give me that answer.
Yeah, she like freaked me out.
Yeah. What's 25 squared? No. 25 times 25? 625? I'll call it. Okay, you paused even longer there. What if I asked you a really hard question, like what's 2 to the 16?
Calculator?
Okay, you see what I did there? Yeah, that's 65,536, right? Yeah, you got it eventually. Okay, well, if the master is the guy controlling the clock, he needs it now. He's going doop, 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 doop. He's expecting data to be there. So how do you tell the professor, the master, see what I did? Students, professor. How do you tell the professor you need more time? Adam just gives me this sort of doe in the headlights look. Think back to that balloon. The clock is an open collector device. It can only release it to 5 volts. It only reads on a high. So if the thing isn't high, it can't read the data. So what do you do if you're the slave device and you need more time? You have to hold the clock low. You have to hold the clock low because you can't hold it high. There's no way to hold anything in this I2C system high. So what you do, here's what the master's trying to do. Okay, he's trying to go high, low, but what he's really saying is 0, Z. The slave, most of the time, is just saying Z. But when he decides he needs more time, the slave pulls the clock line low. So again, you have an aggregate clock line. It's based on the wire anding of both clocks. So this is the time that Adam needs to figure out 2 to the 16. That's how long it takes. Now, it might be an environmental sensor that needs to get some air quality reports, or it needs to stabilize some kind of a temperature sensor, or it needs to do a water analysis. Whatever the sensor is that you're talking to, it needs more time. So you say, hey, give me the latest ozone report. And it says, 1 moment. Okay, here's the number. The air quality is good. I don't know what are the units of air quality?
Yeah.
Parts per million of coal dust or something? Sure, if that's what you're doing. If you're doing a particulate analysis, parts per million. If you're just doing a very objective, it's good today, it's nice out. All right. So once the slave releases it, it's back to Z stated. At that point, the master sees, oh, I'm back to a 1 now, so I'll read the next byte, and then continue on my merry way. So you have this clock stretching. Last question. Let's say it's the day before the exam. You're all my devices, and you both have a question. So you both raise your hands at the same time. You want a shared resource. That's me in this case. So now I'm not the master. I'm actually the wires now. I'm multi-talented. So I'm the wire. How do I choose which person to call on first? It's not a case of you raised your hand and then you raised your hand. I would call on the person who raised their hand first. You raise it at exactly the same time. Like interrupts. Interrupts had a priority to them. It's actually pretty similar. What we do is we do what's called, well, actually in cell phones and RF terminology, there we go. CSMA or CDMA, depending on how you're looking at it. We are, as every time we transmit a bit, we're also looking at the line and ensuring that we transmitted that bit correctly. So I've got a balloon, and I release it, and I make sure it hits the ceiling. If it doesn't hit the ceiling, I don't have to look to my right. I know someone else must be holding it down, right? So that's what we call arbitration. You got two people trying to talk at the same time. So there's their start condition. They both do a start condition at exactly the same time. Then we look at our first data bit. It's the same. So right now, I pulled it low and I look at it and it's low. It's not on the ceiling, so I think that I'm in good shape, even though someone else is also holding on to that string at the same time. Only once somebody tries to release the balloon, because this is the aggregate data line. So I release the balloon and I'm looking for it to hit the ceiling and it doesn't. So at that point I say, oh, somebody else is also on this bus. I will yield to them. The person who tries to release the bus first loses the arbitration. Okay? Because, of course, you've let go of the balloon. They can run off with your balloon. You've lost it. You no longer have control of the balloon. So what does that mean? Since the first thing you're going to be sending after a start condition is what kind of packet? Well, at least we've got it down to one of two things, yeah. The first thing you send after a start condition is a start packet. An address packet, excuse me. Start condition address packet. So what does that mean? If you've got two devices that are trying to talk to two different slaves, who gets priority? We actually saw it when we were looking at doing the wire and. I was looking at device 13, ZZ01, and device 9, 1001. Which came out the end? The 9 came out. The lower number came out. So when you are doing arbitration, it's the idea that the thing that has the lowest address takes priority. Now, we haven't talked about where addresses come from yet. We will. But before we do that, let's switch gears. This has been a lot of physical stuff that's happening. This is the protocol. It's the standard. It has nothing to do with the hardware. So let's look at the I2C unit in the AVR. Here it is. It's so simple. Well, the truth is you can't find an I2C unit inside of the 328P. The I2C unit doesn't exist. And here's why. I2C is a trademarked protocol. Okay, it's trademarked by Philips. They invented it. They trademarked it. You can't use it unless you pay royalties. So instead, Atmel, now Microchip, has a two-wire interface mode. So let me show you the two-wire interface. What? This is my favorite joke. There's actually a thing online now that has indexed every Simpsons episode by frame with the words, with the transcript. So you can search for any words and you can get a frame of that Simpsons episode from when they're saying it. So let's look at the two-wire interface mode, see if we recognize anything. Oh, look, there's an SCL line, an SDA line, an address, a start and stop condition, an arbitration detection. It's almost like this will do exactly the same thing as I²C, but not be called I²C. Funny how that works. Yeah, it's the same thing. All right, it's just it's I²C compatible. All right, so it's got a thing that will generate start and stop conditions. It's got some things like for noise immunity, slew control, spike filter, spike suppression. Okay, here's the actual data register. When you put data into this, that's the data you want to send as a transmitter, not necessarily as a master or a slave, but as a transmitter. It's also where data will appear if you're the receiver. Okay. This address match unit, that's if you're pretending to be a slave device or you're acting as a slave device, that is what address you will respond to. So you can set your own address that you want to listen to. And finally, we've got our standard kind of status registers and control registers. Two-wire interface, because it defines a couple layers of abstraction, is actually the easiest to get going on more advanced systems. So if you're running, say, a Raspberry Pi or a BeagleBone or some kind of embedded Linux computer, I²C is something that you can do from the command line. You just type I²C something something something, and you'll be able to deal with that. Remember when I was talking about Mr. Memory? Did I have that? Did I leave that ink on the slide? Mr. Memory. This whole thing is one command. Read into memory from this. It does both things. It deals with the repeated start, does it all, and it gives it right back to you. I²C is a highly defined protocol across any kind of device. It doesn't have to be just a memory device. It could be a real-time clock, which may come in handy in about half an hour. Okay, so let's continue on here. So there's our two-wire interface unit. Let's get right into the good stuff. The status register. Here are the status bits. They are here. Here are the prescaler bits. There's only two fields. Unlike all of the other peripherals we've talked about up until this point, the status bits are a field. Different combinations give you different results. It's not like this is the receive complete flag and this is the transmit complete flag. No, you just look at this whole thing as one number and then consult a table. We do have fine-grained control over our baud rate. Even though most devices either work at 100 kilohertz or 400 kilohertz, there's now actually a standard for 1 megabit per second, I believe. So those are the three default speeds. You can talk at any speed that is less than the max speed of the device you're working on. If you have different devices on your bus, you got one that can talk at 1 megabit, 3 that can talk at 400 kilohertz. You cannot go faster than the slowest device. So if you have 9 1 megabit per second devices and 1 100 kilohertz, you're limited to 100 kilohertz for everything. Okay? Because the address packet is the first thing that differentiates which one you're talking to. So you've got to deal with that. How do you calculate your baud rate? Well, it's a pretty simple formula. You take whatever these two bits are, and 4 to those prescaler bits gives you your actual prescaler. So what are your possible prescalers? You can have 0, 0, 0, 1, 1, 0, 1, 1. That's 0, 1, 2, 3. So that means that we've got 4 to the 0 is 1, 4 to the 1 is 4, 4 to the 2 is 16, 4 to the 3 is 64, yes. Okay, So those are your possible prescalers. You take your CPU clock frequency, whatever's in the baud rate register, whatever's the prescaler. Done. That's your baud rate. So more often than not, you just want to fix this to one of these numbers and move on with your life. Okay. The address register, TWAR, just says, hey, what is your 7-bit address? And do you answer to a general call? General call is the idea that there's one address reserved for talking to everybody at once. Okay. And do you want to actually answer to that? So the idea is the CPU says, anyone there? Question mark. And if this bit is enabled, someone will say, yep. And that's all they'll say. They'll say, yep. From there, you have to go and figure out what the slave address is of this thing and just talk to it a little bit more in detail. But this at least says, hey, is anybody there? Okay. Okay, the control register has a bunch of bits in it. And the way we're going to talk about this, even though you could create a two-wire interface library that uses interrupt-based systems, you would need to be a bit larger of a state machine because you need to keep track of where you are in the transmission cycle. Are you after the stop bit but before the address packet? Are you after the address packet, so you need to send a data packet? There's all this stuff that needs to go on. Each of these bits means something. Sta is start, sto is stop, en is enable, ea is enable acknowledge. So if you're the receiver, the only thing you're responsible for is the acknowledge bit. And finally, the interrupt flag. This is going to go high anytime something happens. Unlike SPI, which was fairly straightforward, and UART, which was fairly straightforward, when you wanted to send something, you just put a byte in some register, and it started shooting bits out serially. I2C is the most complicated protocol we're going to talk about in terms of how to get stuff up and running, because there are so many parts of the packet and so many parts of the transmission. So right out of the data sheet, here we go. First thing we do is a start condition. To make a start condition, you write to the control register. You say, I want to create a start condition by not only turning on the start bit, but also a few other bits. And we'll get to what those bits are. Then you sit there and you wait. Okay? You sit there and you wait until the interrupt flag is set. At which point you look at the status register to see if the start condition actually worked. Because it's possible at any one of these points for it to fail. Now, depending on how robust your library is, maybe you skip these status checks. And that may or may not come back to haunt you later. So, every time this little black block appears, that's the interrupt flag being set. So it's set after the start condition is sent. SLA plus write, that's slave address plus the read-write bit. And then there's the acknowledge bit. Once that whole packet has been sent, the interrupt flag is sent again. And you should once again check the status register to make sure everything went okay. What could have gone wrong while transmitting the slave address plus write? A write. From where? Well, so if you get past this point, you have control of the bus, don't you? Except for one case. What happens if two devices put a start condition at the same time? The lower, that's arbitration. Well, arbitration occurs here. This is where arbitration happens. Okay? So, if you lose arbitration, the status register would tell you about that. Okay? If you lost arbitration, you stop. You don't continue. Okay? But if everything is fine and you're still good, then you send data. And once that data byte plus the acknowledge has happened, you get another interrupt. Then you have to send a stop condition. And here's one of the extra weird things about the way the two-wire interface on the AVR works. You don't get a confirmation that the stop condition has happened. Okay, much like Dr. Evil, you just throw it out there and assume it all went according to plan. I've never been comfortable with this, but it's never caused me a problem. But you don't actually get a confirmation that the stop condition has occurred. It's just how they chose to implement it. So, for the most basic of packet, slave address and then data packet, you've got 3 different steps. Wait for the start condition, wait for the address packet, wait for the data packet, and then your final step is turn the start condition on. Now, how do you do all of this? Well, you do it with these different bits in the control register. We'll go over that in a second, how you deal with this. But first, before you do anything, you do have to turn this thing on. You have to initialize it with all the appropriate values. So in terms of if you are a master device, you got to set the clock frequency. That's the first thing. That involves the baud register and the prescaler bits. They're in the status register. And then you have to turn the whole thing on. So you turn on the enable. That's it to initialize. It's relatively straightforward. You do a little bit of calculation beforehand and you're done. Everything else gets a little bit wonky. To transmit a start condition, you say TW control register equals TW enable ORed with TW start ORed with TW int. So it's a little strange. Okay, we don't do or equals in this because it just slows us down. We're just going to overwrite the control register every time we want something to happen. So we got to leave it on. To turn the start condition, we have to both start and set the interrupt bit high. If you were to immediately read the control register right after you did this, you would not see the interrupt bit high. Okay, it's one of those weird hardware mapped registers that has special purposes built in. So this is how you create a start condition. If we were building up an abstraction library, you might have something that says TW underscore start condition. And this would be all that's in it. But it abstracts away all of the registers. So that's the start condition. To send the data, you first put it into the data register, but nothing happens. So once you put it in there, you can spend days just pondering your navel. Only when you turn on the enable and the interrupt bits will it actually start pumping bits out of the device serially. And again, you have to sit here and wait for the interrupt flag to go high. Same with the start condition. You have to sit there and poll for TW int. Okay, now that's if you're a master and you're sending data. If you are a master and you are receiving data, you turn on the enable, the interrupt, and that's it. Okay, it's the same. The only difference is you read at the end of this. Now, since the protocol to start it is the same, how does the processor know whether it should be receiving data or transmitting data? Yeah, and that's why it's kind of difficult to write an interrupt-driven routine. Arduino has actually done it. They have a very nice I2C library. They call it the wire library. I don't know why they didn't call it the two-wire interface library, but they didn't. So because of the slave address plus the read-or-write bit, the TWI interface keeps track of that. It knows that you sent out a write address packet. So it's going to take the data out of the data register and send it serially. If you put a read bit into the address packet, it knows that it's going to be sampling the data line. Okay? The last thing to do is the stop condition, which involves writing a 1 to the enable, to the stop it, and to the interrupt. And you do not poll. You just assume that it happened. I'm not going to spend a whole lot of time talking about slave mode programming because that's really beyond the scope of our course. I want to get right into a type of I2C device called a real-time clock. Real-time clock is really nifty. It has its own crystal. It has its own battery, usually some kind of a coin cell. Okay? And it keeps highly accurate time. And not only does it keep highly accurate time, it acts as a calendar. You tell it, hey, today is November 21st, 2017. It's 10:31 and 5 seconds in the morning. Okay? And it's a Tuesday. And it will keep track of all of the things. It'll keep track of leap years, I believe. All this kind of stuff. It'll keep it in there. And then later on, you can ask it, hey, what is the date today? And it will tell you. Even if you've got this connected to some kind of battery that has a switch on it, you can completely power down this whole device. Okay? Cut power off to everything. Because it's got a battery backup, it will always remember. This one coin cell battery will last several years, I think. 3 years, something like that, depending on how often you deal with it. Now, the way we access this is we treat it as if it was a memory device. Okay? We have a bunch of bytes that we can access. First thing I want to call to your attention is this hard line right down the middle. Everything is stored in binary coded decimal. So if you're looking at the number of seconds, and the number of seconds is 53, that is stored as hex 53. Which means it's very easy to split this up and turn it into a 7-segment display number. Because it's not stored in binary, it's stored in BCD. Now, you had to deal with splitting nibbles up, second lab, right? So you know how to split nibbles up. In later labs, you had to divide by 10 and divide by 100 and so forth. We did that in something. I know I went through that with somebody. That was the most recent lab. To display the number? Yeah. So that was harder because you had to do division. This does not require any division. It just involves splitting up nibbles. It's one of the advantages of BCD. So since you have to display the time on a clock, it's good that this is all BCD. So, things that we need to know here. Each byte of address means something different. Address 0 is the seconds. Address 1 is the minutes. Address 2 is the hours. Now, depending on if you want to look at it as 12 or 24 hour time, call that military time or standard time. My watch right now says 10:34. In 4 hours, it'll say 14:34. A regular watch won't say 14:34. It'll say 2:34 p.m. So depending on how you're looking at this, it'll show either AM, PM, or 24-hour time. It shows the day, and the day is a number between 1 and 7. That's Sunday, Monday, Tuesday, Wednesday. The next address is the date. That's the day of month. And it'll keep track of whether February has 28 or 29 days. It'll keep track of what days have 30 or 31 days. The month, again, split into BCD. The months could go from month 1 to 12. So that's stored in BCD. So there's your tens digit of your month. The year, it only keeps track of 2 digits of year. So it's susceptible to Y2K type problems, right? It doesn't keep a full 2017. It only keeps 0 to 99. We will not be using exactly this memory map because we're going to not be using the DS1307. We're going to be using the DS3231. Okay, data sheets in the M drive. It is extremely similar. It's just even more accurate. and it has built-in alarm controls, okay, which is pretty good. All right, so that's what's going on. You treat this like a memory. So that same sequence of Mr. Memory, set your pointer to 0, and then read 3 bytes would apply if you wanted to know the seconds, minutes, and hours. Because there is a register pointer. And that's the only thing that you write to. First, you write to the register pointer, and then any additional writes will overwrite the time. If you want to read from a random location, random access, first you write the pointer, and then you do a repeated start, and then you do another read. Now, we didn't actually talk about how to create a repeated start condition, did we? That's because to create a repeated start, it's the same as a start condition. So if you want to do a repeated start, you just say start, the same way that you do a regular start. So the most basic way of talking to the 1307 is you must first transmit a start condition. You must transmit the address of the 1307. Now that is the address of the 1307, okay? The only way to find that out is to look at the data sheet, okay? And you say a 0 because you want to write to the address pointer. So then you send as a data packet the address. If you want to write over those values, you keep sending bytes. You don't need a repeated start condition. The first byte goes into the register pointer. The rest of the bytes will start at that register location and keep overwriting. And finally, do a stop condition. If you want to do just a read, you transmit a start condition, transmit the address in a 1, and you receive as many bytes as you want. Now, that assumes that the register pointer is already where you want it to be. If you wanted to read from a particular location, you would first have to do a start condition, an address with a write, overwrite the register pointer, repeated start, transmit the address again, and then read as many bytes as you wanted. Okay, so how are you going to go about approaching this design? Let's go to the data sheet. First off, you should consult the data sheet. First off, figure out where are the SCL and the SDA pins. That's important. You should go over and peruse. Oh, you can't see. You can't peruse. Full screen projector preview. There we go. That's better. So you should figure out where the SDA and SCL bits are. There they are. You should go and you should peruse the 2-wire serial interface module. Notice it says it is compatible with Philips I2C protocol. Note the apostrophe there denoting ownership of I2C. I'm surprised they didn't put a trademark there. Maybe I'm misrecollecting. Maybe it's not trademarked, it's patented. Either way, Philips owns it. Okay, I haven't had to look at the legal part of this for a while, but they own it. You can't use I2C without giving them credit. But you can say that it's compatible with them without giving credit. So the 328p maxes out at 400 kilohertz. You should take a look at this. You'll notice where many of my figures came from. All right, it's all in here, all of it, each and every little thing. What it also shows you, however, and this is sort of the nice thing, is it gives you code, right? It gives you sample code. How do you create a start condition? There it is. How do you wait for the int flag to be set? There it is. It also does some interesting stuff here. It says, hey, status register ended with F8 not equal to start. What the hell is all that about? Well, where's my pencil? F8 is 11111000. If you go over to the register description for the status register, you'll see that we only want to look at those bits. So it masks out, what the heck is going on here? It masks out the lower bits. It masks out the prescaler bits and that unused bit. So you only get those. Now, what does a start actually look like? Well, in order to do that, you have to consult the datasheet even more. Come on. Come on. All right, so here it says, hey, does it equal to start? If it doesn't equal start, show an error. Well, we're going to look at that now. Here is a table, status codes for master transmitter. So you could be master transmitter or master receiver. You could be slave transmitter or slave receiver. So this table is for master transmitter mode. So you have to check, hey, does the status register equal 8? That means that a successful start condition has been transmitted. If you get a 10, that means it looks like a repeated start. So those two are what you would get after a start. And it tells you, hey, your next step is put some data onto the into the data register. Then the next thing you have to look at, hey, did my slave address plus write get transmitted? Either I received an acknowledge or I received a not acknowledge. That's for a write. Also, if you keep going, there is a data byte. Data byte has been transmitted and an acknowledge has been received. Or a data byte has been transmitted and a not acknowledge has been received. Other things can happen. You can lose arbitration. Okay? So then there's some flowcharts that show you how stuff works. This is for, again, only master transmitter mode. So you don't see any reading here. Okay? To do reading, you have to go to another table. Status codes for master receiver. Start conditions look the same. But now we've got lost arbitration in read. Slave address plus read has been transmitted. It's different status codes. Data bytes received in receiver mode have different status codes. Okay. And here's how it would all work out. This is kind of all the different possibilities. Along the top, that's a perfectly successful transmission. Or we could say, hey, we didn't get an acknowledge, so therefore we're going to leave. Okay, or we lost arbitration, so we're going to leave. Okay, so all of these things could happen along with their different devices. But the nice part about all of this is it does give you, hey, here's the sample code you need to actually do this. Okay, now if you just remove these boxes that check for error, it'll still run, you just won't know if something bad has happened. So that's something to keep in mind here, that when you're first developing this library, it might behoove you to look at these bits. Because I guarantee you're going to come up to me, you're going to say, it's not working, we can't figure out why it's not working. And I'm going to say, okay, stop right here. Tell me what the status bits say. And they're not going to correspond to that table. So if you're programming with I2C and you don't have this data sheet open to look at what's going to happen, you're screwed. The other thing you really need to look at here in manuals is the data sheet for the DS3231. Extremely accurate I2C. They paid the money. They paid the money to Philips. So they get to use I2C. So you need to look at how does this physically connect. Now, fortunately, I'm giving you a breakout board that has pull-up resistors already on it. Okay? What you're looking for is not really the electrical characteristics, but block diagrams are always helpful. What's going on inside of this? Okay, there's some interrupt pins that might be useful. And this is what open collector looks like. It can only drive low. It can't drive high. Pin descriptions are useful. What I want, though, This right here. Here's the table of all of the addresses. So this does a bit more. The first couple of bytes are the current time plus the century. So this one will actually keep track of what century you're in, either the current century or the next century. All right, in even or odd century. It will also keep track of the alarm. You have one alarm and then a second alarm. So since you're building an alarm clock, you might want to look at this as an option. Doesn't mean you have to use it. You can create your own alarm. All right. There are a bunch of control bits which you need to pay attention to. You need to read up on these. What do? All right. And then there's verbiage. You should read the whole thing because it tells you what do the different alarm masks mean and so on. Just anything else I want to talk about here? Not really. Okay. It even gives you like this is how you're supposed to communicate, and it's exactly as you'd expect. A start condition, a slave address. Also, buried in these diagrams somewhere is the real slave address of this device. You have to find that because it is not the same as the 1307. Usually, it would sit right up in front, but if it doesn't, you've got to look for it, okay? Because that's the first thing you need. Interesting, I can't find it. I know it's in here. I2C interface, DS1331, I2C interface. Ain't nobody got time for that. Find me address. Address map. Address is written. BCC is applied. Yeah. Okay, so where is the actual? Let's look for 011. I have a fair chance of finding that. There it is. Oh, no, that's the temperature range. Oh, I was so close. Can't find it. Let's try 01. Nope. I mean, normally I would just sit down and read this as a matter of course. Oh, that's January. Here, okay, there. This was what I was looking for. This is how you should write data to it. How you should write multiple data bytes to it and so forth. It gives you the slave address right here. I must have skipped over this at some point. So this is a good model to follow. Okay, when you want to do something, start condition, it tells you, hey, who's generating this? The master is generating this information. The slave generates the acknowledge. Or if you are doing a data read, you say, hey, I want to do a read, so you put a 1, and then it sends all of this data, and you acknowledge it, except for when you're done, when you say don't acknowledge it. That's an A with a bar over it. And there are even more. If you want to do a random access read, you do a write to a particular address. You say repeated start, and then you do a read of as many bytes as you want. So next class, I know we're just about done, right? We're a little bit past time. Next class, we're going to build up some library functions, just like we did with SPI, so that we can communicate with the real-time clock. All right? And that would be, let's just check our syllabus here. Fall 17. Syllabus. What's a syllabus? That's Miss Frizzle's bus. That's a silly bus. Where are we? So I'm not going to see you for the rest of the week, right? So there'll be no lab because class is canceled. It's Thanksgiving. That doesn't mean you shouldn't work on it. Okay? Just because you don't have lab this week doesn't mean you can forget about lab. Okay? We'll talk about I²C one more time, and our last lecture will be the one that I'll test you the least on, because you're going to spend all of 388 working on how to control motors and how to talk to devices and how to control things with transistors. All right, but this is going to give you a base of understanding for what you're trying to do there. We'll review for the final on December 5th. The makeup exam, if you missed an exam, is on the 7th. The final is 8 a.m. the 12th. The December 7th will be a makeup lab where you can demo your alarm. So you'll have this week to work on your lab, next week to work on your lab, and you can demo it as late as the last day of our classes, but I need the report by that day. And then it's final. You guys have made it through the wilderness, as they say in the song. You are engineers, so maybe the rest of the song applies too. Talk to you later.